Hello, Mrs. Suggs here with video number 14 on the spectra. I hope to explain several illustrations to you to give you a deeper understanding of this complex topic of how we get spectra from atoms. One thing I want to make very clear right here in the beginning. Here I have a dish with the salt in it. This salt is not giving off any color, because these atoms bonded together to make this salt have not been excited yet. You need to excite these atoms by pouring in methanol and igniting it before the atoms give off light that we then analyze. Likewise, this is a tube of gas. This is a tube of hydrogen. This tube of hydrogen is not giving off any colored light. It has to be excited by putting electricity through these two ends, getting the atoms excited, giving them energy, and then the hydrogen will give off color as it releases energy. I will switch to my slides. In this video, I hope that you, forget these objectives. These are the wrong objectives. I'll go over at the end what I want you to be able to learn, but you don't need your class packet or your homework packet. I'm just trying to give you a lecture with some clearer background. So, the development of the new atomic model. The emission of light is fundamentally related to the behavior of electrons in atoms. Just read that again. Here is my objective: to describe the relationship between electrons and emitted light by excited atoms using the Bohr model of the atom, from flame tests to bright line emission spectra. Remember that we are in progression of looking at the development of atomic theory. Rutherford was so important in discovering this nucleus as the densely populated area of protons, he didn't know about neutrons, in the center of the atom. But Rutherford had no idea about the electrons and their locations. He just assumed they were throughout the rest of the volume of the atom. The gold foil experiment delineated the small, compact, positive nucleus. But it was the Bohr model that talked about electrons and where they existed. This Bohr model quantized energy levels as the location of where electrons exist. We do need to remember that we're not done. It is not until the next chapter that we get into this quantum mechanical model of the atom. Here are the two videos that I will also post in Schoology. They're worth 11 minutes of your time. From flame tests to bright line emission spectra. I'm going to be going through the diagrams that I said were so important in your book. The first diagram on the properties of light was just illustrating that light is more complex than we imagine. It has all these different frequencies of wavelengths beyond the small visible spectrum here between 400 and 700 nanometers. These two equations are highlighted in your book as we have done calculations with them. The speed of light equals frequency times wavelength, and energy is directly proportional via Planck's constant to frequency. As you look at neon lights, which are the red lights that you see around buildings, it's interesting to know that this looks like one color. If it were a flame test, you would see just the one gross color. But if you look at these neon lights with a diffraction grating, as we have here in the classroom, you would see that this red neon light given off by excited neon atoms is actually very specific wavelengths and frequencies that we call the bright line emission spectra. You only get this combination of colors with neon. Page 101. If you were to excite a tube of hydrogen, like this tube that I have right here, you would see that it also glows to give off what looks like one color. But if that color is separated by the use of a prism, you would see the 4 bright lines in the hydrogen emission spectra. It is because of an electron that has been excited up to a higher energy level. They're calling this energy level number 2. When an electron has been excited up to here, but it falls back down to the lower energy level, that is when the photon is emitted. The atom has to take in energy to go up to a higher energy level, and the electron gives off energy as it falls to the lower energy level. Remember, this light can be called photons. Photons are the packets of energy that have characteristic wavelengths and frequencies. So these 2 pictures on page 102 are essential. Here we have the Here we have light coming in and hitting an electron in the first energy level, E equals 1. That electron is flying up to the second energy level. The reason the electron rose from energy level 1 to energy level 2 is because it absorbed a photon of energy. Now, once an electron is at a higher energy level, it can fall back down to any of the lower energy levels and give off energy or a photon. This absorption by taking in energy and emission by giving off energy is an important understanding. I'm going to skip that right now. So here we have hydrogen being excited by passing a current of electricity through it. That excited hydrogen has a very specific bright line emission spectra as given off here. A red, a teal, and 2 purple lines. If you were to look at mercury, neon, and helium, there are unique spectral lines given off by those excited atoms. Hence, we come to call the bright line emission spectra fingerprints of the atoms. These 2 types of spectra are mirror images of each other. I have shown you the emission of light when electrons fall from the excited state down to what we call ground level, lower energy states. But we can reverse that process. We can shine continuous spectrum into an atom and see which specific light it absorbs. When we're measuring the fact that hydrogen would absorb red light, teal light, and a couple of purple energies, then we would be seeing these black lines against a rainbow of all color, being the absorption spectra. Emission and absorption spectra are the opposite of each other. The emission spectra of elements are unique because the energies of the electron energy levels are unique for each element. Listen to that again. The emission spectra of elements are unique because the energy levels of the electron energy levels are unique for each element. There's nothing special about the electron itself. Electrons are all the same, but where those electrons exist in the unique energy levels gives a unique fingerprint of emission spectra for every element. I have a periodic table on Schoology where you can go and click every element and see its emission spectra. Now, sometimes you see energy levels diagrammed as a ladder instead of rings, and both are useful. This ladder configuration means that the ground energy state where an electron can exist is down here. This is energy level n equals 1. You would have to imagine the nucleus down several floors below this classroom. If this is the first energy level where an electron can exist, we call it the ground state. The second energy level would be here, the third, the fourth, the fifth. These are the spacings of the energy levels in this theoretical atom. It is that spacing that is unique for each element. It's also true that energy levels are in the beginning very far apart, and then as you go to higher and higher energy levels, the energy levels get closer and closer. This is an important understanding as we continue our study of the atom. Now in physics, we would call these energy levels electron volts to describe the amount of energy on each energy level. Here in chemistry, we would describe them with joules. Remember, when an electron is in a lower energy level, to go higher, it must absorb energy. That would give you an absorption spectra. You'd be missing a color of light. If that excited electron falls down to a lower energy level, light is given off. But it is a unique color of light that's both absorbed and released depending on the difference between these two energy levels. There is a unique energy to n equals 1, energy level n equals 1. There is a unique energy to energy level number 2. The difference in those two energies is the energy of the light given off. So you can see here that if an electron is excited to a particular energy level, it absorbs a unique energy of light. But if that excited electron falls back down to the ground state, it releases a unique energy or color of light. So here are 4 hydrogen atoms. And what I want to show you is the light that's emitted from a hydrogen atom is because an excited electron goes from level 6 to level 2 or level 5. Oops, this isn't going to work. Level 5 to level 2. Nope, I won't be able to do this on this board right now. Excited electrons in hydrogen can fall from energy level 6 to 2, 5 to 2, 4 to 2, or 3 to 2. It is those 4 energy transitions that give off the 4 bright line emission spectra of hydrogen. So here I have these 2 pictures right next to each other. The ladder configuration, where you can see that the spacing between energy levels, energy level 1, 2, 3, 4, is unique, and the spacing is farther and farther apart. Here I've drawn the concentric circles as Bohr often drew them, wanting you to see that the energy levels get closer and closer together as you go away from the nucleus to the 1st, 2nd, 3rd, and 4th energy level. So the big red slide, energy levels in atoms of different elements are uniquely spaced. So here you could see that this might be one element. This would be a different element. This would be a different element. And likewise, this last would be a uniquely different element. This provides the fact that when electrons transition between these uniquely spaced energy levels, a unique spectra of light is given off, as opposed to the electron transitions of excited electrons in these other 3 atoms. It is the spacing of the energy levels that produces a change in energy, giving a unique spectra to each element. So do you understand the Bohr model of the atom? Do you recognize that transitions of electrons within the atom due to the absorbing or emitting of energy gives rise to the absorption or the emission spectra? Can you describe how the bright line emission spectra are unique for every element and therefore called the fingerprints of the atom? I hope that this illustration or explanation of some of these illustrations helps you better go back and try to understand even more deeply Bohr's model of the atom. And next week, we continue with the quantum mechanical model. Thank you. Best to you.